Welcome to the second video in our discussion series about acids and bases. For this video, we will be discussing conjugate acid-base pairs. So in the previous video, we have defined the Bronsted-Lowry acid and bases. Now, when a Bronsted-Lowry acid reacts with a Bronsted-Lowry base, a proton is transferred from the acid to the base. So the Bronsted-Lowry acid donates a proton to the Bronsted-Lowry base which accepts it. Consider this example, the reaction of the general acid HA with the general base B, and in an acid-base reaction, one bond is broken from the reactants and then one bond is formed from the products. So the electron pair of the base B forms a new bond to the proton of the acid, forming HB. So the acid HA loses a proton, leaving the electron pair in the HA bond on A, forming the A ion. So the product formed from a loss of proton, which is here, the product formed by loss of a proton from an acid is called its conjugate base, while the product formed by a gain of proton by a base is called its conjugate acid. Thus, in this example, the conjugate base of the acid HA is A ion, while the conjugate acid of the base B is HB in the product. So that's how we identify the conjugate acid-base pair. Remember that the product formed by loss of a proton from an acid is called its conjugate base, while the product formed by a gain of a proton by a base is called its conjugate base. So another example here would be the reaction between hydrobromic acid and water, forming bromide ion and hydronium ion. So when hydrobromic acid is dissolved in water, for example, HBr loses a proton to form its conjugate base, bromide ion. And the base water here gains a proton to form the hydronium ion. Thus, hydrobromic acid and bromide ion is the conjugate acid-base pair, while water and hydronium ion is also a conjugate base pair because these are two species because these two species differ by the presence of a proton as well. So the net charge must be the same on both sides of the equation. So consider the following examples here and let's identify the conjugate acid-base pairs. So to find the conjugate pairs, we find the species that donated hydrogen ion and the species that accepted it, which will serve as the base. So the acid donates a hydrogen ion to become its conjugate base, and the base accepts a hydrogen ion to become its conjugate acid. So in the first example, as you can see here, H2PO4 donated a hydrogen ion, forming its conjugate base, HPO4. And then we have here the base, which is CO3, and on the product side, it accepted the hydrogen ion, therefore forming the conjugate acid of the base CO3. So in this example, the conjugate acid-base pairs are H2PO4 and HPO4, and then the other pair would be CO3 and HCO3. For the next example, we have here the reaction between water and sulfate forming hydroxide and sulfuric acid. So in this case, as you can see, water served as an acid because it donated a proton, forming its conjugate base OH, while SO3 served as a base, forming the conjugate acid HSO3 from the reaction. So the conjugate acid-base pair are H2O and OH, and SO3 and HSO3. Now, we can also identify the net direction of reaction. So the net direction of an acid-base reaction depends on the relative strength of the acids and bases involved. So we have to remember that a reaction will favor the formation of the weaker acid and the base. So in this example, we have here a hydrosulfuric acid and ammonia, which are strong acid and a strong base. So it will form hydrogen sulfide and ammonium ion, which are weaker base and weaker acid. So based from this reaction, since the weaker acid and weaker base is in the product side, this reaction now will favor the formation of the product or driving the reaction to the right. So how will we know if these are strong acids or strong bases, or weaker acids or weaker bases? We can base the strength of the acids and bases involved in the reaction by using this table, which can be found in your book. So we have here the acid strength going up and then the base strength going down. So we can refer to this diagram when determining the strength of the conjugate acid-base pair. Okay, so let's work on some examples. Predict the net direction and whether K sub C is greater or less than 1 for each of the following reaction, and assume equal initial concentration of all species. So we have here H2PO4 and NH3 forming HPO4 and NH4. And then for the second example, we have H2O and HS forming OH and H2S. So our plan is to identify the conjugate acid-base pairs and consult the previous figure to see which acid and base are stronger. Now, if we will look at the chemical equation, we can determine here, and based on our previous diagram, that H2PO4 is a stronger acid as well as NH3 being a stronger base. So in that case, the products will be the weaker base and the weaker acid. For this scenario, the net direction for this reaction is to the right, so K sub C is greater than 1. For the second example, we have the weaker acids and the weaker bases on the left side or on the reactant side. That's why the net direction for this reaction is to the left, so K sub C is less than 1. So in our previous example, you have seen that water can either be an acid or a base. So when a substance like water serves as an acid or a base, we call that an amphoteric compound. When we say amphoteric compound, it is a compound that contains both a hydrogen atom and a lone pair of electrons, and it can be either an acid or a base. As I have said earlier, water can act as a base, and then it can also accept another hydrogen atom, forming a conjugate acid. So we have here the hydronium ion, while water can also serve as an acid as well. So it can remove one of its hydrogen atoms, forming hydroxide ion or the conjugate base. And that's it for our second part of the lecture video. Thank you for listening.